So, hello everyone, and welcome to this PowerSys webinar. So for a bit of context, let me first introduce you to PowerSys. We are a global electrical engineering software and services provider, offering fully customized solutions to help our customers solve their complex electrification challenges in EV and grid. Our solution includes electrical engineering expertise, simulation software, and power computing. For more than 20 years now, PowerSys has been delivering its expertise to thousands of customers all around the world. And in 2023, it acquired Simba, the new generation simulation software for power electronics. During today's webinar, we will be exploring a novel approach to power semiconductor simulation, accuracy and speed without compromise. It is my pleasure to introduce and give a warm welcome to our speakers for today. So firstly, Adrien Michel. Adrien received his engineering degree in 2015 and has been working at PowerSys since 2016. He's taking care of Simba support. And secondly, Anup Kumar Singh. He received his PhD degree in the field of power electronics in November 2021, and he works at PowerSys as a power electronics application engineer. He's also a member of the development team for Simba. Lastly, all questions will be answered during the Q&A session at the end of this webinar. You will also receive a short questionnaire at the end of this session, and we thank you in advance for all of you who will take the time to give us their feedback, because this is very helpful for us to better develop our webinars. So without further ado, please join me in welcoming Adrien.
Thank you, Stephanie. Thank you, Anup. Thank you, everyone. Nice to meet you, everyone. Thanks for joining our webinar today. We are really excited to show you what we have done in the latest release from 2308, from August, I mean. So I will start to present this webinar, and then Anup, my colleague based in India, will directly talk about some use cases as well. So we are happy to show you these new features, and I am sure you will find as well very useful and interesting for your power electronic simulation needs. So today, as you know, the goal of the webinar is to show you the new detailed semiconductor models that we have developed in order to both be really accurate, like the datasheet, or like you can find in SPICE simulation software, and also to be the fastest one. So these are our global goal. So my colleague Stephanie has already introduced PowerSys, so I will not do it anymore. So these are basically our content of the webinar today. So I am going to introduce you quickly Simba, because maybe most of you don't know really what is Simba, what you can do, and how it can be a really powerful partner for your needs. I will also dig into the latest release features. So all the new features that we have directly that are available in the latest version. And then we are going to show you some use cases about semiconductor models. So we are going through a double pulse test, which is common used simulation. We are going to introduce a buck converter with real detailed MOSFET and diodes. And also we are going to introduce the EMI capabilities in Simba. And finally, we will conclude with a small conclusion. And I think you will see directly what you can do and how it can help you to simulate any power converter simulation. So I will go through the slide, and just I will show you this slide. So as you can see, as you have seen, we are providing expertise in electrical engineering. You can also use our cluster to parallelize, to simulate any circuits. Okay, so we can provide you power computing solution, and also our business is also dedicated to simulation software. And as you can see, our two main products are GMAG and Simba. So GMAG is a finite element analysis software for mechanical design, for motor design, basically, and Simba, which is in fact linked to power electronic simulation and motor drive. So for GMAG, we are the distributor, the reseller, but for Simba, we are not only the reseller, we are the exclusive developer. So for Simba, we develop, we are the main developer, and we also distribute it. So this is a new thing for us, for PowerSys, because we have acquired Simba a few months ago, and now we have all the decision about what Simba can be for the future, depending on your feedback, on your roadmap, because as you know, we have a public roadmap for Simba. So it was just to introduce the GMAG and the Simba link because I am going to introduce you these features soon. So what is Simba? As you may know, Simba is a power electronic simulation software with an amazing speed, accuracy, and simplicity. Maybe most of you have already gave a trial, and maybe you have also found the same feedback as we used to receive. So our solver, our algorithms used in Simba allows you to make a very fast and with an amazing speed. So in that case, you will save your time because you will not spend a lot of hours to simulate. Also, the accuracy that we provide in Simba is more and more improved with our new detailed switching model. So in that case, you can use ideal model or real one. And also the simplicity of the graphical user interface, as you can see on the screen now. As you can see, you don't have a lot of buttons. You have few windows. You can easily build your power converters. Click on just one button, this one, in order to simulate and retrieve the result into the result tab directly here. So in few steps, in few minutes, you can easily build your own circuit, tune it and simulate, choose which solver, which time step you want to use, and at the end, everything will be done automatically. The time step will be automatically tuned by the solver and so on. So this our main goal, and this is what we want to, and this is how we achieve Simba. So when you do power electronic simulation, you need and you will directly cover all these kind of topics. First, you will need to design your system. You will need to think about which kind of topology I want to create, I want to implement. You will need maybe, for example, first to make some mathematical equation in order to first have a quick idea about which value for any semiconductors you will need to use, which value for your inductor, capacitor, filters, and so on. Okay, you can also perform some thermal analysis if you want to calculate the efficiency, for example. So you will need to work in first in the system design in level system simulation. Then another team can work into control design because control and power electronics are two different things. Okay, and control is really important. So when you do control, you will need to make your open loop first, and then you will need to close it. You will need to make a closed control loop, okay, in order to get something accurate and stable. And for that, you will need to set up some analysis, like AC analysis, in order to check the body plot. You will need to maybe to use C code if you want to use C code as well. So this is the main goal of the control design. It will perform your control loop, as you can see here, which is quite famous picture. Then you have, in the next step, you need to go in the design of gate driver and EMI filter. This is common process when you do this kind of simulation. So in that case, you need to design your PCB, you need to design your gate driver, for example, to define your EMI filter and to calculate the noises. Okay? And basically, when you have done this kind of work, you can go to the magnetics design and also to the real controller software and hardware. If you want to make some simulation in the loop, hardware in a loop, generate code, and put your code inside a microcontroller and check the real behavior of your control stage. And actually, so until today, Simba is focused on those three topics: system design, control design, and gate driver and EMI design. So we are actually, Simba is good and is focused for this kind of topics. And we plan in the future to go through magnetics and also hardware in a loop simulation. This is planned in our roadmap and this is what we want to do. But today, if you are only interested and if you are focused to, or if you are focusing inside system design, simulate quickly a topology, estimate the losses, the junction temperature, make any control loop, and calculate your EMI filters, you can do that with Simba. And we are good in this kind of process. And finally, we want to cover all, as you can see, the magnetics and this kind of real hardware simulation. Also, as you may know, we have three ways to use Simba. The first one is to use the desktop version. So this is the graphical user interface that you can see here on the top of the screen. And this is one of the most common use of Simba. So any people are going to download Simba from our website and they can just download the exe file, the application. You can launch it in your desktop, in your computer, and then you can start to build any circuit from scratch directly. This is the desktop version. You have also the online version, which is linked to your browser. So you can go on Google and you can have access also to Simba if you want to simulate quickly some topologies as well. And you have the final one, which is one of the most important one, which is a Python module. Because as you know, we have added the capability to Simba to be used with Python interface. So it means you can build any circuit from scratch. You can simulate any circuit from Simba in Python. This is the API Python module. So maybe most of you have already used it in order to perform a lot of powerful simulation, advanced simulation, and you can combine both the use of Simba desktop and Python in order to make a very powerful and amazing system. If you want to make some robust analysis, advanced analysis, if you want to emulate a kind of oscilloscope, if you want to use some predefined algorithm in Python in order to build and to calculate for you any controller, it is possible. We have done a lot of tutorials and application case on Python, so you can find them inside Simba website. So feel free to go to our website and to check what we can do, what you can do with both Python and Simba. So now I am going to introduce you the last features of the last version of Simba from 2308 from August. So this is a quick video. So first, as you may know, you can use and build your own subcircuits. Okay, it was already available, but now you can define a new variable or some variables inside the subcircuit in order, for example, if you want to build maybe 10 subcircuit with 10 different value, you can do that by using this kind of capability. So for example, if you copy and paste your subcircuit, you can directly modify the variable directly of the resistance. I mean, you can modify the resistance and the capacitance value by giving directly a name. And then you don't need to go each time inside the subcircuit and modify this and this. We just need to give the same name, which is R, and then the resistance R will be reused inside the subcircuit because it will be a name. Okay, so you can do that. Also, we have introduced the capability to use the parameter file as well. So you can now add a kind of txt file, and inside the txt file, you can define any parameters. So as you can see on this example, we have defined all the parameters with the design variable window. So you can introduce DCV, which is the input voltage of your system, and it is 600. I'm sorry. But if you don't want to use this kind of panel in Simba, you can directly curate a kind of txt file and put the path of this file. And then Simba will read the file with all the variable defined inside it. Thanks to that, you can maybe make a kind of parametric simulation only by using this file and sweep a lot of different txt file as well. It's possible to do this kind of simulation. So basically, we have just defined variable inside subcircuit to better organize them. Okay. Then we have also introduced the link between Gmag and Simba. So maybe most of you are working with mechanical teams because maybe you are focusing on motor drive simulation, and maybe your colleagues use Gmag itself or Gmag Express. This is the online version of Gmag, which is free. You can go on Gmag website, create an account, and have access to Gmag Express in order to build your own, for example, PMSM and export this RT file, okay, in order to use it later in Simba. Or you can use Gmag, which is, the 3D mechanical simulation software, build your own motor inside it, and use Gmag RT tool in order to extract the RT file. So again, Gmag RT allows you to build a kind of lookup table in order to take into account, as you can see, the total flux, the inductance value, the torque, the iron losses, and even more parameters could be used inside Gmag-RT table. So the goal, in fact, is to build your own 3D mechanical super accurate motor in Gmag and to click into one button in order to export the same 3D motor, but it will be in lookup table, 2D lookup table, as you can see here. And you will have a lot of data, a lot of column will be gathered inside the lookup table RTT file. And then this model will have the same, almost the same accuracy as the real motor defined in Gmag. And then you can reuse it inside Simba in order to make a real motor drive simulation. And as you can see, we have compute the simulation in few seconds, and you can directly, if you want, calculate the efficiency. It could be the efficiency of your inverter, it could be the efficiency of your motor. So here, this is what I have shown you a few seconds ago. This is the PMSM examples that I am talking. We have just set up one inverter, actually, with ideal model for now. And also you can compute the losses because we have the capability to compute directly the losses of your IGBTs directly from the ideal semiconductors model. Okay. And here, in that case, we have used a motor, a Gmag-RT motor, a PMSM1. And this file is, as you can see, coming from my computer, and this is in fact a RTT file. This is the extension provided by Gmag-RT when you produce, when you create, when you generate your lookup table with real data. And then all the control stage has been done with the ID, IQ reference in order to create VD and VQ signals, and then build your own PWM signal in order to turn on and turn off your semiconductors. Okay, so this is a basic motor drive simulation that you can do, but now you don't need to use ideal model. You can do that with ideal PMSM, but now you can use a real Gmag-RT model. And you can click on this simulate button, and as you can see, the simulation is quite fast. And in the meantime, you can go into the result tab and you can observe directly all the scopes which have been enabled during the simulation. So for example, here I can check the torque. Okay, so this is the torque produced by the motor. You can also check the current, three-phase inverter current, which are feeding directly the motor here. You can also, if you prefer, add a new chart and add the current inside the chart directly here. You can make a quick zoom and understand directly the ripple, the ringing, and so on. Okay, so you can check this kind of behavior. You can check the torque, and as you can see, the torque has a non-linear behavior. Why? Because the G-McGarty model is a non-linear one. It is a real model. So of course, the non-linearity, sorry, will be there. So this is, yes, what you can do now with Gmag. And then this is the next step of the webinar, and the main step is to use real semiconductors. And inside the next simulation, this one, I use real MOSFET in order to get real behavior of your inverter, and also the real model of your PMSM. So in that case, now you don't need to use Gmag RT model with ideal. You can now use real detailed MOSFET inside Simba plus real motor model in order to have a full real simulation. And this is the main goal of this simulation. But I am going to introduce the real detailed MOSFET soon. But here it was just show you that it is not restricted to ideal semiconductor model plus motor. You can do both real semiconductors and real mechanical things. And you can compute the full and the total efficiency map of your drive, as well as you can see on the screen at the bottom here. Also, one new features is the capability to compute faster the stop at steady state function. As you know, in Simba, you have the capability to define an end time. Okay, so maybe you want to simulate maybe 50 milliseconds. But if you don't know how much time it will take to simulate, in that case, you can click on this handy button, stop at steady state, which has already created few years ago. Okay, it is not a new feature, this stop at steady state, but it was already there. And the simulation will stop itself when the steady state is detected. In that case, you don't need to take care about which end time you need to put. But the new features which has been added are the base frequency, the number of base period, and the save initial point. So, for example, if you use the base period, these parameters will help the algorithm to detect easily and in a faster way the stop at steady state. I will show you that. Then, if you want to only show the 3 or 5 or maybe only the last period in the steady state, you just need to put these parameters at the numbers that you want. Maybe you are only taking care about the steady state and you want to check only the 10 last period in your simulation in order to check the average losses or average current and so on. You can just put 10 and then it will directly show you the 10 last period based on this base frequency, which here in fact mostly use, which is in fact the switching frequency of your system. It could be the switching frequency, or it could be directly the 50 or 60 hertz, as you know, and it will be in fact the fundamental frequency of the harmonics, okay, of your FFT. And also you can decide to save the initial point or not. It means if you have a huge current or huge voltage at t is equal to 0, okay, at the initial time, you can just disable it if you don't want to get this kind of really high value in terms of current or voltage, for example. So by default, it is always saved. It means you will retrieve all the results at the first initial point. But if you don't want to save it, you can just disable it and it will just start at the first next time step. So I can show you quickly one example. So I can just click on Start window. It will just open a new welcome page of Simba. You can click on Design Example. You can click on Buck like this. You can see you can simulate during 20 milliseconds. You can check the uh, output voltage, which is directly here. You can decide to stop now the simulation at steady state. In that case, as you can see, it is not 20 milliseconds. Okay, so you can directly retrieve the first simulation, which was the 20 milliseconds. Now this is with the stop at steady state, and the switching frequency of my bug is 5K. So you can decide to set at, okay, the base frequency is 5K or 5,000, let's say, it's the same. And now, as you can see, we have the new directly simulation time, which has been directly provided here. Okay, and basically you can also provide maybe the free last period to observe, and now you can simulate, and you can see now the free last period of your system. Okay, so if you don't put that, in that case, you can just put like this, and you will see that with the 5K frequency, the steady state has been detected in this point. And this point was just with the norm with the first 20 milliseconds. Okay, so if you use these parameters, it will just help the system to find the steady state sooner. And if you want to display only the free last period, like this, in that case, I can just stop. And here you can see the free last period of your steady state. And we have also added some very interesting function, like if you want to use the drag and drop one, you don't need to click on plus. When you select your component, you can just drag and drop it. If you double click on all your gsimba files, Simba will be open automatically. So the association between Simba and the gsimba, the project file, have been done. We have an auto backup function. It means if your computer crash for any reason, you can just retrieve your last simulation with your last parameters that you have configured. So you will not lose everything, basically. And we have added a lot of new blocks, as you can see here, if you want to, again, perform more simulation. And the main milestone, the main topic of this new release is the release of new detailed diode and MOSFET for switching transient behavior. So the goal, in fact, is to be the most accurate as possible, okay, as a reality. So based on that, we think that the datasheet of the manufacturer who provide any semiconductors is in fact what we need to rely on in order to make something accurate. So basically, we have built those two new semiconductors model in order to be in the real world, in order to simulate very accurately and without losing the speed. So I will just detail that in a few seconds. Just a quick introduction about the semiconductors model. Most of the time, you need to think about, should I keep the best accuracy for my system, or should I be the fastest one? And this is always the main trade-off that you need to perform when you do power electronics simulation. So sometimes you will need to use some SPICE solver simulation software, like LT-SPICE, like P-SPICE, like Symmetrix, like you have a lot of different SPICE based from NG SPICE, which is the main original SPICE solver. And if you do that, you will maybe mostly interested in real behavior of your semiconductors, of your transient behavior. And this kind of simulation, most of the time, could are very long because you need to have a detailed model, and it can be very long simulation. But sometimes if you want to go fast and you don't take care so much about a real model, you can use more or less an ideal or quasi ideal simulation software like, PSIM, Plex, Simscape, and some other. So this trade-off, in fact, is a very pain for you because each time you need to use two simulation software. You need to reproduce one circuit from one software into another one. It will take some time. It can also lead to some human errors or to some issue between each solver used in those simulation software. And at the end, it is not really convenient to work in two different software. Also, if you have a big team and everyone needs to work in two simulation software, and at the end, it is completely not convenient. And our goal with Simba is to combine both accuracy and calculation speed. So actually, you can use Simba for ideal simulation, for system level simulation, and it will use ideal model. And you can use, of course, thermal data, thermal lookup table that you can import directly from the semiconductors of manufacturer. But now you can use our detailed model. It is called SPICE-like. Okay, this is detailed model in order to be as accurate as possible as SPICE. So again, SPICE, sometimes it is not always accurate. And this is why we have added two possibilities. One is to use the datasheet information, to scan the datasheet in order to represent the real behavior, transient and static behavior. And one other is to use some SPICE, netlist SPICE model in order to use them inside Simba. And it is SPICE-like because we have built an algorithm in order to reuse and recalculate SPICE parameters netlist inside Simba in order to be accurate as much as possible as SPICE. So now Simba combine both device level simulation and system level simulation. Okay, and this is what we have done for this new semiconductors model. So the goal is to capture the switching and the static characteristic, okay, with a precise, super fast, and ideal, and they are used, in fact, in a extensive iterative calculation. For example, if you want to use Python, you can sweep 1,000 of semiconductors and check the influence of the parameters, okay, on your simulation. And again, everything will be always with the same solver. You don't have to change between Simba solver or SPICE solver. It is not working like this. It is always Simba solver, but the way we have built those models will be really, really fast. And I am showing to show you this. So the process is quite easy. You need to, for the MOSFET, you need to fill in the gate resistance value. So you can just open the datasheet and get the value. Then you need to put the transfer characteristic, for example, ID versus VGS on this corner here at one transfer characteristics value. For example, for VDS is equal to 20. Then you need also to put one output characteristics, ID versus VDS, okay, for one VGS value. You can choose any VGS value and any output characteristics, but only one needs to be filled in inside the table here. And then Simba will do all the process for you. You need to put also the nonlinear capacitance. You know, CISS, COSS, and CRSS versus VDS. As you know, those typical curve. You can just scan it or import a CSV file. And the last one is a body diode that you need to fill in. You know, the body main curve, as you can see in the fourth quadrant. Okay, so once you have done that, your detailed model is characterized, and you can start to run it. And here, what we have done is you can here check the internal model of our detailed MOSFET. So we have introduced some nonlinear capacitance. We have also introduced a body diode. So use with a real detailed diode as well. We have put the gate resistance. You can see here the nonlinear capacitance, the mathematics. And here, this is the inherent calculation of the MOSFET in cutoff region, ohmic region, and saturation. And what we have done is we have built a kind of we have built and used a kind of algorithm which can help you to detect the main MOSFET channel parameters in order to calculate automatically those three parameters, VTH, K, and lambda. And then Simba will use those parameters in order to compute the switching and the transient behavior. And as you may know, those parameters are most of the time used in SPICE as well. So we are going to extract those. So we can also extract those parameters from SPICE and put them inside Simba in order to reproduce also the same behavior as SPICE. So basically, you have the choice to use MOSFET model from datasheet. You just need to use those kind of characteristics, and Simba will do it. We do everything automatically. And in fact, we have built two use cases to show you the detailed model based on the datasheet, and one other based on SPICE model. So here you can just see the result between Simba and the datasheet once you have scanned the main characteristics that I showed you in order to put them inside the detailed MOSFET. We have made a double plus test, and here this is the result of the same double plus test, sorry, but it will compare Simba result versus SPICE. And as you can see, the result is the same. So if you, for example, want to use a SPICE model, and if you also use one SPICE simulation software, another simulation software to make your system level simulation, and if you think that it is really a pain to do that in two different simulation software to reproduce everything and to lose time, at the end, you will need to use Simba because Simba will help you and will do that for you. So I can directly open the Python script because, as you know, Simba is compatible with Python. So basically, we have built this kind of Python script, which is not too long. We have only 200 lines. Okay, and if you run this script step by step, we are going to compute and to simulate this double plus test. Okay, so in fact, Simba simulation will be done automatically. It will be initialized. We are going also to import some datasheet parameters, some datasheet value, and we are going to merge both results, one from Simba and one other from the datasheet. And I think it takes sometimes because I am in Zoom. But anyway, as you can see, the simulation is done, and you can see that the result between Simba and the datasheet. So the solid one is Simba, and with a small dash is the datasheet. So as you can see, we have very accurate results. You can see here the ID versus VGS result between Simba in blue and the datasheet in red. And it is, yeah, it will show you the rest. It takes just a few seconds. And here you can see the drain current, you can see the drain source voltage and the gate source voltage, the result of the double pulse test. And here, now, maybe, okay, I can show you, I can close this interactive window and I can resimulate the same thing now. Okay, yeah, between Simba, because we have introduced the SPICE detailed model with the SPICE VDMOS features. And we are going to compare this new model versus SPICE simulation. So again, we have run the LT-SPICE simulation. We have exported the result because you can use the LT-SPICE library in Python. You can use our Simba Python library, and you can combine both in order to compute and to, as you can see, we have set up 900 simulation in less than 13 seconds. So it is, so with Python, it is extremely fast. And you can see now the result between Simba, this is the solid curve, and the dash curve, which is the LT-SPICE. So as you can see, we are matching perfectly. We have the same characteristics, ID versus VGS, it is the same. So I can zoom, can click on this zoom, and you can see the results, which are very, very close. You can see the gate voltage, the drain source voltage again. So here we have just made a different initialization. This is why we have different value here, just for the initialization. And the drain current as well, which are very the same. I need to zoom, and you can see the result between both. And if you, yeah, one thing I forgot is to show you the Miller plateau, which is just there. And you can see now the Miller plateau between Simba and SPICE with our new detailed model based on SPICE parameters. So basically, you have the choice to use detailed MOSFET based on the datasheet, which will give you the same accuracy as the datasheet, or if you prefer to rely on SPICE model because you work with SPICE, in that case, you can use our SPICE VDMOS. And this result is, in fact, what I have shown you just there in this Python script. And the first Python script was the same simulation, but we have used this detailed MOSFET based on the datasheet where you need to scan, all the characteristics. Non-linear capacitance, ID, VGS, VDS, and so on. So now you can use Simba for this kind of real simulation if you want, or you can use also with system level simulation as well. You have both the capability. So now I am going to give the ball to my colleague Anup. Then he can introduce you the other test case that we have done in order to show you how it works. So Anup, I will just stop to share my screen and you can continue.
Thank you, Adrian. Thank you. So I'll share my screen. Okay, I'll brief you about the two test cases, which on which I have used the detailed models. The first one is the bug control. So I'll directly open the model to show how you can model the detailed using detailed device. So here you can see this is a buck converter, and which is first made with ideal components, and then have introduced some parasitics into this, and then this is also with ideal model. I mean ideal semiconductor models. Then after that, here I have replaced the models with the detailed models. Actually, this example was done by my colleague Carol in US. So yeah, so this is done. So I'll just simulate these models and tell you the difference. We can see the difference directly. So you can see this is completed. So here you can see the detailed model. So I'll look into the inductor current and then VDS. So here you can see. So first of all, it is into the DCM till it gets stabilized uh, and into continuous conduction mode. Okay, so this is with the ideal, all the ideal switches. Now, if we look, I'll just run this buck converter with detailed model. Okay, so if I'll run this, wait, yep. So I'll take a new window. PDS, yes. So here you can see. So till it is in discontinuous mode, if I'll zoom it, okay. And then yeah, here you can see. So here the ringing effect you can see very well, which is due to the parasitics that you have added and the detailed device models. Okay. So then after this, the further you can see also the ringing effect, which you can see here. If I'll zoom in. So here in the using the ideal model, you don't see any ringing effect. And with ideal models, you can see the ringing because in the design itself, it is coming a second order circuit. This you can model a lead inductance, and inside the capacitance parasitics will be there. And then there is some source to damp that oscillation. So further, your device selection and all these things will depend on this ringing effect. So this, if it is more, you need to put extra snubber circuit. So that is also nothing but you just need to damp these oscillations. Okay, so in this way, this device models and all these things, detailed device models will be helpful for you. So generally, you don't need to go to for detailed model to another software for system level simulation, another software. You can do everything right here in Simba. Okay, so if you look at the steady state voltage, the output voltage, so here you can see this. Yeah, so if you can, so here 39.5 volts and this 40 volts. So although it is it's almost same, since it is in open loop, otherwise you would have got the same results. Okay. So yeah, so this is about the this example that we have made is using this detailed semiconductor models, what Adrian has explained. Generally, whatever the curves that you provide here. So based on this, there is a curve fitting algorithm which is fitted into this into the simulation engine, and then it detects the three values, the three characteristics, the channel characteristics value, that is K, lambda, and VGS. So once it gets those values, so then it can calculate and it can give you the value in three regions. So three regions, what are the regions are saturation, ohmic, and cutoff region. So it detects in which region it is operating, and then based on those channel parameters, it calculates and gives you the values. So it is pretty fast. So as you can see this. So the next use case that I want to show you is about the EMI analysis. You can perform the EMI analysis as well using these detailed device models. So for that, okay. So the same. So this is the buck converter, which is somewhat different from the previous one. So here the buck converter, I have added few parasitics, lead inductance here for the drain, and yeah. And this is in closed loop, which is a peak current mode control. So this model, this example I have developed. And here for to do the EMI analysis, you need basically three things. The first one is the detailed device models. The second thing is you need to know the listen block to measure the EMI. That too at what standard that you want to measure. So for that, yeah, the listen has to be built. Okay. And then the third one is the signal measurement. So once you get the signal from this listen, so how you identify which one is the common mode, what is the differential mode noise, and then EMI noise. So these are nothing but the listen is just using this kind of filter. So here you can see, so one filter you put in the line and then neutral, and then you take the signal out to measure the measurements. Okay, so and then here you can see the signal measurements, and these are nothing but so if you go to fundamental, then you will know like how the common mode noise can be extracted, uh, and differential, I mean the differential mode signals can be extracted. So this is just a mathematical calculations. Okay, so to view the analysis in detail, so again I'll use the Python module as our software supports the Python interfacing. So I'll just open this Python one. So here first of all I'll run this script which is without filter. Okay, we can wait for the simulation to run. It will take around 15 to I think 20 seconds to run this simulation, and then we can see the affected curves. Here, one more thing. This is put between direct listen. I'm measuring for the AC input signal. Okay, from here the signal is going, and then I'm using a diode bridge to rectify the signal, and then this DC link capacitor, and then it is supplying to the buck converter. Okay, and these capacitors are the common, you can say the parasitics, the common mode capacitors, which are there maybe in between these two, and this is the chassis ground. So these are modeled. So I have used around uh, around C1 around 11 common mode capacitors, and then to replicate the behavior, like how it can behave to generate the common mode noise. Okay, so here you can see. So you can see here, this is the time domain result. So these noise, common mode noise, differential mode noise, and EMI noise in time domain. And then if you convert this into frequency domain, you can see this is the CISPR22 standards. So as you can see, it is crossing the limit. So this is not as so you can say that this buck converter is not compatible with this CISPR22 standard. So now what you need to do, you need to design an EMI filter which can suppress this noise and can stay within the limits, within this CISPR22 limits. Okay, so so for that you need to design an EMI filter. So I have designed one simple EMI filter which is of L type. You can say L type filter. So this is the filter that you can design. So here you can see three things are important in this EMI filter. The first one is the X-rated capacitor, which is generally connected between line to neutral. And then there's this common mode choke. So I have modeled the common mode choke using coupled inductor, which is available in Simba. And then you can say the Y-rated capacitor, so which is generally connected between the line or neutral to the chassis ground. Okay, so so you can tune these three parameters. So so this value, the common mode values, and then again capacitor. So generally this XR accelerated capacitors you can tune to reduce the differential mode noise. Common mode choke and the common mode capacitors you can tune to reduce the common mode noise. This is one simple example using L-type filter. So based on your complexity of your models or something, you can use various different types of filters. So okay, so that also the filter design you can see here. So so at what limit, at what frequency, how much dB it is crossing. So you can note down that particular dB, and then you can take those values. You can write the equations, and to attenuate those, how much coefficients are needed for that particular type of filter. You may require the filter, maybe not. You may need to maybe more than one or two filter in series, two or three filters. So it depends, like what is your modeling, what is your complexity, and or what is your needs, and what standards you need to mitigate. Okay. So now next, after designing this filter, so I'll just use this buck EMI with filter. So I have once I have done this. Okay. So here it will be run different window. Okay, so regarding the script, so I have done everything here in the GUI. I have made the model. And here also you can run it, no issues, but you can take the signals in Python domain and you can do the post processing. So that's what I have done here. And in the script, what I have done here, this is the Python library that we are using, and this matplotlib to do the results to plot it, and NumPy to do some mathematical calculations. So what calculations I have done? So here I have taken the signals. So I'm performing the FFT on the signal data that I have. So this FFT is just I'm using this NumPy to measure the FFT on the signals. And here, since this is the EMI analysis, so I need to look the results in dB microvolts. So I just changed the scale of the y-axis in dB microvolts, and then CISPR22 standards I added, and then you can plot the results based on. Okay, so here you can see. So after filter design, you can see the results in time domain. You can clearly see the difference. And then in frequency domain, if you calculate the FFT on that particular signals, so you can see these noise are well within the limits. Okay, so after designing that simple L-type filter on that particular buck connector, now you are able to mitigate those noise. And now you can say this, yeah, now the design filter is as per the EMI standards. What standard? It is CISPR22. So as in the same way, you can perform the analysis for various standards. You can do various other things. So all this is possible because of the models here, as you can see. So other things are based on all linear elements and mathematical calculations that you can do by yourself. Okay, so yeah, so this is how you can do various analysis using new features that have developed, and we have came up with in 23 version. Okay, I think yes. Next one. This is the MOSFET model IRF 540N that is used for this buck converter. Okay, so this is what I have explained. This is the EMI example that I have taken. So this MOSFET, the data that I have taken is not exactly this one. It is some of the data that I've used. And then these are the blocks that we have seen. And this is the detailed MOSFET model. Here the results is simulated without EMI filter. And then the next one is when we have added this L-type filter, you can see the difference clearly. So now you are this is well within the limits. Okay, so semiconductor models, for the semiconductor models, we still have some next steps. We are still validating the models, and then we'll finalize it. So some validation is still going on. We will be adding scopes for PDS, VGS, ID, and instantaneous power to look into it. Okay, not only this, if you have the waveform from this MOSFET model. Okay, so the waveform, and you have the ID and VDS curves exactly, and then you can get the power losses accurate, which can be very accurate. You just integrate the overlapping area between VDS and IDS. The switching losses you'll be able to calculate very accurately. Not only switching losses, the conduction losses also you'll be able to do it. And then capability to import diode, MOSFET, and sub-circuit from SPICE. So I think I have seen some question in Q&A section. So someone was asking if we can import .sub-CKT from SPICE. So as of now, it is not there, but we are doing that. So soon, very soon, maybe next 1 month, you'll be able to import all these 3 things from the SPICE directly. And then there's introduce options to define initial voltage values for CGS and CDS. So for this also, you'll be unable to, sometimes you may need to define these things for your accurate analysis. So this also will make it enabled for you to do this. And then ability to add extra body diodes, output and transfer characteristics under various temperatures and voltage conditions. Okay, so the temperature dependent characteristics we are implementing. So one question is also that I have seen. So the temperature dependent characteristics of your device will be added. But although, yeah, you can add discrete. I mean, at one temperature, you can add one curve. Even now, you can take it you can take it in Python, you can automate it, and you can sweep for different temperatures. That is possible as of now. But inherent characteristics, which the temperature dependent characteristics, we will implement it soon. Okay. And then based on the real time junction temperature, your channel characteristics changes, or generally, which is the case. So that will be implemented. And then we'll generate models at different temperatures. So all these things will be possible. So these things are under validation and in progress, and soon it will be. So in conclusion, so what we have seen the MOSFET and diode detailed models, which are available for realistic switching transient behavior. So for this, you can do everything at one place. You don't need another solver for your detailed device models. And then asim.simba Python library. So Python module, it allows you to automate your design, your power converter design. There are no limits, anything you can do. So once you take our power electronic system or design in Python domain, you can do anything you want with the results, with the any logics that you want to, any decision making you can do based on the results that you are getting from the Python, from the power electronic converter or system design. And many technical resources are available to get started with Simba, and worldwide trainings are available, and we have very aggressive and open roadmap. So you can find it here on GitHub. So you can participate in our roadmap, which is a public roadmap, any features that you want us to develop for you. So that also you can request, or you found any bug, or you want to report anything, you can participate in this using this particular link. And Simba is now an all-in-one software which allows both device and system level simulation. So as Adrian have already shown, we are into the next step will be the magnetic modeling, and the final step of this software will be to do the HIL and SIL simulation. So everything will be possible in Simba. So thank you, everyone. So now we can go for the Q&A session.
Okay, thank you, Anup.
We have
Should I read all the questions, Anup? Would you like I read them?
Yes.
Okay.
Yes.
So I think the first question has been answered already by you regarding the subcircuit behavior model. So it will be available soon.
Yes, and in the second part of first question, can I introduce tolerance to the models? Yeah, we have examples on Monte Carlo analysis in the website, so you can have a look at that, how we have implemented that. So by that, you need to automate your design using Python. So you just make the tolerances of your particular elements, maybe normal distribution or uniform distribution, and then you can generate the random values for that particular, and you can do the analysis. That is possible, yes.
Yeah. And you can download the Monte Carlo Python script in our simba.io website. It will be available to test. Then the temperature dependent. Also, Anup, you already answered to him. So actually it is single one, but we will plan to do it for various. But you can build maybe 10 single model with 10 different temperature. You can sweep them in Python as well. It's possible to do this kind of workaround for now. Is it possible to encrypt models in Simba? Actually, right now, no, it's not possible. But this is, I think, one feature that we can implement and add into our roadmap if it is something interesting for you. So it is feasible. Okay.
For sharing purpose, if you want, you can use this Python Jupyter notebook, which maybe in somehow you can encrypt that. Not the Simba models, but yeah, you can do that encryption. So maybe in future we can try to that .gsimba file encryption of that particular.
Then, is there any special motors library available in Simba, like stepper motors or servo motors? Actually, in Simba, we do have BLDC, so brushless DC motor, squirrel cage induction machine, PMSM, and synchronous reluctance machine model, and the Jimagerty PMSM1. So if again you need a special motor for your needs that is not included in Simba, we can of course build it and add it into the library. But actually we don't have this kind of motors. As I have mentioned, we have BLDC, squirrel cage, PMSM, and synchronous reluctance machine.
Yeah, but we can work on this if you have
Yeah.
special request, or we can develop it for you, just like we did for one of for our customers. So BLDC also we developed
Yeah.
for our customer, and Scenario motor, which is also very good. So we developed all these motors for our customers. So if you want us to develop, you can go to that particular link. You can provide
Go in
the
GitHub.
roadmap, or you can get back to us directly. So we work on it, and then we can provide these motor models.
Then, can models developed in Simba be integrated with Simulink? It depends what you want to do. If you talk about FMI, functional mockup interface, this is also something what we want to release next year in order to encapsulate, model into a FMU and reuse this FMU into another software like Simulink or any other one. So we plan to do that. But actually, what you can do is to use Python, and you can run Simba directly from MATLAB. So if you make your Simba circuit in Simba, you can go into MATLAB and run it directly from MATLAB and reuse MATLAB function. But in that case, you will need to use Python to do that. So yeah.
Yes, that's next one is there a link between thermal modeling and electrical modeling? Example, does the characteristics of MOSFET changes automatically when temperature increases? So I think I have explained it just now. If temperature dependent models are separate previously. As of now, it is not there. So it is separate. The electrical is separate. Thermal is separate based on the lookup table. But as I told you, using PWL MOSFETs, you can take it in Simba, do the post-processing on your results, integrate the overlapping, which will give you the real-time, say, the real-time energy losses, okay, which will be quite accurate. And but yeah, it is not temperature dependent as of now. We will make it. As you have seen, what we are doing now in the roadmap soon for this. So we will do that. Temperature dependent,
Exactly.
Which will be the electrical characteristics. Generally, your based on temperature changes, basically your curves will deviate what you define. Okay, so that deviation in real time, we'll try to.
Then, is it possible to generate power electronics faults in simulation? Yes, you can do that. And we have done also a Python script. So if you go again into our simba.io website, you can directly go to the Monte Carlo, to the sensitivity analysis, and we have built a very super interesting fault analysis simulation. And even a all-in-one combined simulation, fault, Monte Carlo, and sensitivity in the same Python script. So you can do that, and we have built some of Python script for doing this. So you can also go through. With which semiconductors manufacturer are you working with? Actually, we are working. We are in relation and in discussion with some of them in order maybe to build a kind of standard, maybe. But actually, we don't have any contract with them. Okay, you can go on any power manufacturer of semiconductors and download a model. So basically for the thermal capabilities, as you know, you can do thermal simulation in Simba. You just need to go into the, maybe it's just a name. It could be on Infineon, it could be ROM, it could be Volspeed, it could be Cree, it could be any of those manufacturers. And you just need to download the XML file. You know, this is the electro-thermal model in order to compute the losses. So as you maybe do for SPICE, you are going to go to the website of the manufacturer. You are going to looking for the SPICE model. Sometimes you can also look for the XML file, and those XML will contain all the data to compute the losses. So what you can do actually is go on any power semi on in any power in any semiconductors website and download the XML file and import it in order to compute the losses.
Okay, so the next one is, do you give training specific to fundamentals of power electronics like DC-DC converter, DC-AC converter, DC-AC converters, BESS, motor controllers? So all the power electronic topics he has included. And maybe we can have sessions on specific topics with Simba. Yes, you can get back to us regarding requirements. So we can provide you training. We can discuss on it. You can get back to us for this request. Generally, we can do that. Issues. Okay, cost for one license. For the cost, actually you can contact our marketing and sales team, so they will tell you the accurate price. Generally, it is somewhere in the range of 5K to 6K euros for one perpetual license. But exact pricing, you can get back to our marketing and sales team, so they will let you know.
If you're interested, we can just send us an email and we can check your configuration and we will send you a price. Okay? Yep.
Okay, so thank you for your interesting webinar regarding the accurate simulation models of electronic devices. Could you please provide us with such startup Python course that can be used as a basis for any future applications? Yes, we have done recently the training, Python training, which was covering. If you don't know anything on Python, you can start with Python, some basics on Python. What are the things, data structures, basis required to do the analysis? All the things we have covered in that, and then how it can be advanced. I mean, to use into application, into power, especially in power electronics application. So everything is there. So those recordings are also available. So those you can have a look at it. And if you want further information or further, or if you want some training from us further, can say the customized training for you. So in that case also you can reach out to us.
Yeah. So just was something. So you can see the Simba.io website. Okay. And if you go into the technical resources, you will have all the tutorials that we have built with the main functionalities that you can find in the desktop version. Some advanced and basic examples that you can download as well, and also Python example. So if you go on tutorial, if you want to have a quick look on how the Python module is working, you can directly click on Get Started with Python module. You can also check the multi-process because you can parallelize simulation with Python. You can have access to Jupyter notebook file for interactive simulation file. You can do a lot of things, parameter sweep, AC sweep, C code. You can even debug the C code. Now, if you are only interested in Python code, you can go in Python example here, and you can download all those examples. You have the fault, you have Monte Carlo sensitivity, you can sweep any semiconductors and make a kind of benchmark of thermal data. Okay, you can do multi-core or multi-thread if you want. You can do anything with Python and Simba. We have also done a webinar based on Python 3 months ago. So if you go on YouTube and look for the PowerSys Simba channel, you will have access to all the video and recordings that we have done. But definitely, as Anoop said, we have some training available, and we can also make some training for you according to your needs. Everything is possible with us and with Simba.
Yes, we are very flexible here. So, is it possible to design three-phase active neutral point clamped inverter in Simba? Yes, it is possible. Any topology, any power converter topology, control design, a detail level system design, detail, semiconductor model. So anything is possible, except magnetic design and hardware. Okay, is soft switching possible? Yes. We have example on LLC resonant converter, as you can see on the screen, LLC converter design. So there we have used soft switching. So yeah, soft switching means for with the ideal, you may be struggle, you may struggle to find how the soft switching is happening, but with the detailed models, you can definitely replicate that soft switching. But this example on LLC resonant converter, you can have access to it. You just replace the devices with your actual devices, and then you can analyze this soft switching behavior. It's possible. And then, is it possible to perform reliability analysis and lifetime estimation by some pre-built blocks in the simulation software? Reliability analysis and lifetime estimation, as of now, it is not there. But the workaround can be done. So if you have data, pre-built blocks, as of now it is not there. But if you know how, how many the number of cycles, its use cases, and all these things, the data basically, if you know the dynamics, so you can implement it. You can, as I said, you can do the post processing of the things that is available in GUI. So you can make the system level design, and then the number of times that you want to run it, and each time how it is affecting, how the number of run is affecting your particular device, and then you can perform the reliability analysis, because for each devices there will be some lifetime prediction will be there. So it's at that level you can do that. The workaround is possible, but directly built-in blocks are not there.
If you have your own logic or your own algorithm that you can find maybe on Google or maybe find on Python library, you can try to implement it in Python in order to say maybe this component will lose in terms of capacity, in terms of normal value, and then you can maybe can do this kind of workaround in order to estimate. But we don't have a ready function yet. But we are also working on AI, on these kind of topics, on machine learning as well. So this is something very interesting.
Yes, I think we are through. So we have answered all the questions.
Yeah. I think, yes, everything has been answered. So thank you, everyone. Thank you, Anoop. Thank you, Stephanie. Thank you, all the team. If you don't have any other question right now, we can stop the session. And if you have any other question later, or if you want to make a trial, feel free to contact Anoop and me, or even the marketing team. So anyone at PowerSys, and then we will be in touch all together, and we can make a quick demo as well, and we can introduce any features if you are interested in. Yeah, machine library. Yeah, as I told you, for machine library, if you are interested in any typical model, we can work all together and we can introduce what you want. We have our own roadmap, but if you have any other idea, you can share with us, and we will see how to integrate that in the Simba library.
It's more machine libraries. Machine means like electrical machines, I think. So motor models and machine libraries. Yeah, we are upgrading. So it will be available.
Yeah.
So just now we have added the LDC motors. So the next one may be the stepper motor or some other motors, maybe DC-DC motors also. The DC motors also there in the roadmap, so which will be added in the next release. So yeah, we are upgrading our libraries to this.
Yep.
Thank you, Akshay. Thanks for attending our webinar. And thank you, everyone. Thank you.
Yeah. Thank you for all your words, and feel free to come back to us if you have any other question later. Thank you, everyone. Thank you for attending again, and maybe we can close the session. Thank you, Anup.
Thank you again. Thank you.
Yeah.
Thank you.
Bye-bye, everyone. Thank you. Bye-bye.